Hello everyone. Here we are going to prove that the center of the dihedral group Dn is singleton R0 when n is odd, and it is the set R0 and R180 degrees when n is even. Okay, so first let's understand what this Dn is. Dn is the set of all symmetries of an n-sided regular polygon. Okay, and this will consist of rotations and reflections. Okay, now this rotations I am going to denote by R, and the reflections I will denote by F. Okay, now this subscript I will use to denote the angle of rotation. Say for example, if I am denoting R0, then that will mean it is a rotation by 0 degrees, and R120 will mean that it is rotation by 120 degrees in the anti-clockwise or counterclockwise direction. Okay, now what is the center? Center of a group G is equal to set of all elements A in G such that it commutes with every other elements, right? So given any x in G, Ax must be equal to Xa. All right. So let's find out what the center of Dn is. All right. So for that, first let's pick a rotation. Okay. Let R be a rotation. So I am checking if this rotation can be there in the center or not. So for that, I need to understand how this rotation R will behave with other rotations and with reflections, right? I have to check if this R will commute with other rotations and if it will commute with other reflections as well. So that is the first thing. So uh, let R prime be any other rotation. Be any rotation. Okay. Be any rotation. Then my claim is that R into R prime will be same as R prime into R. Now, why is this so? Now, consider Dn. Okay. In that, consider the rotation by 360 divided by n. Okay, now let's pause this for a minute. Let's take an example and understand this. So consider T3, that is set of all symmetries of a equilateral triangle. Okay, now in this what will be n? It is equal to 3. Now, so what are we considering here? We are considering R 360 divided by 3, which is nothing but R 120 degree. Now what are other rotations here? We have R 240 and we also have R 360, which is nothing but the identity element R0, right? Okay, so what is this R240? To get R240, it is enough for me to take this R120 and do it twice, right? It is composing. It is R120 composed with R120. Am I right? Because first we will rotate by 120 and again we will rotate by 120. So it is net, we are rotating by 240 degrees, right? So it is nothing but R120 square, right? And similarly here I will have R120 cube, right? We will take R120 and I will reflect the I will rotate the entire triangle like by 120 degrees 3 times. Then I will get R360, nothing but, which is nothing but R0, right? So this example I have taken just for you to understand, but in general in Dn, any rotation any rotation will be some power of this R 360 divided by n. Okay, so consider R 360 divided by n. Any rotation will be some power of this. Say now suppose I am calling it to be rho. Then this R which I had begun with, this R will be rho power m for some m. Okay, and this r prime will be rho power n for some n. Okay, so this r prime will nothing be but r rho power m into rho power n, which is nothing but this is of course composition, but this will again be rho power m plus n, right? This I can write this as rho power n plus m, which is nothing but r prime with r, right? So this r and r prime will commute. So if I am taking a rotation r, it will commute with any other rotation. Okay, a rotation r will commute with any other, any rotation. Need of not need of saying other, because of course the rotation r will commute with itself also. So a rotation r will commute with any rotation r prime. Okay, so a rotation r behaves very well with rotations, other rotations. Okay, now let's understand how this r will behave with a reflection. Okay, so now let r be a rotation. This I am retain. Okay, let r be a rotation, and let f be a reflection. Okay, let f be a reflection. Now let's consider this rf. Okay, now we know that dn is a group, so it is closed, so rf will be an element in dn. But rf, it can be rotation or it can be reflection. At this moment we don't know, right? We know it will be some element of dn, so it has to be either rotation or reflection. Okay, so it can be either rotation or it will be reflection. Now let's inspect what is happening. Can it be rotation or not? Suppose RF is a rotation. Okay, suppose. Then we will have that RF will be equal to some R prime. Okay. Now I can undo this rotation R, right? That is R inverse will exist. So I will multiply by R inverse on both sides. So we will have F will be equal to R inverse times R prime. Okay, now this r inverse is also some rotation, right? So it is like some other rotation, say for example s into some r prime, where s is also rotation and r prime is also rotation. Now again it will look like something like this, right? Rho power, so it will again be something like rho power p into rho power what n, which is equal to rho power p plus n and something like that. Now that is what I'm saying is composition of rotations is again a rotation, right? Am I right? So here we began with rf is equal to being some rotation r prime. Then r inverse will exist, and we know that to undo a rotation we can again get we are actually using a rotation itself, right? You can geometrically visualize that. So r inverse must also be some rotation. Okay, so we will have f is equal to r inverse into r prime. So here we are having a composition of rotations, and again it has to be some rotation, right? So we will get that f is a rotation. So all this, what is the conclusion we are getting? F is a rotation. But that is not possible, right? Because we had begun with f being a reflection. So f cannot be a rotation. So this is a contradiction. It's a contradiction, right? So RF cannot be a rotation. RF has to be a reflection. So we have that RF is a reflection. Okay, RF is a reflection. All right. Now, what are the properties of reflection? We know that the inverse of a reflection is itself. Inverse of a reflection, say mu, is itself, right? So we will have that RF, the whole inverse, will be equal to RF. Am I right? But then we know we can apply the properties, the shoe socks property and things like that. And we will have that this is actually nothing but F inverse into R inverse, right? Now, what is this F inverse? F is a reflection. So F inverse must be F itself, right? So this will be F into R inverse since F is a reflection. F is reflection. F inverse will be equal to, okay. Now, as of now, what do we have? These two must be the same, right? We just have that RF is equal to FR inverse. This much we have. Okay. Now, suppose that so far we have not told anything about the commuting, right? Now, suppose that R is commuting with F. Suppose that R commutes with F. Okay, then what will we have? Then we will have that RF must be equal to FR. Okay, so here we had one equation, call it 1. Here we have 2. So from 1 and 2, what do we have? We have that FR must be equal to FR inverse. Okay, now we can cancel F by the cancellation property in groups. So by left cancellation property, we will have that R will be equal to R inverse. Okay, so suppose that R is commuting, then commuting with F, then R must satisfy this property. Okay, R must be equal to R inverse. So what are the elements R that have this property? That means it is R0 and R180. Okay, so what am I saying? So suppose R commutes with F, then R is equal to R0 or R180. Now, R0 will exist for any n. Now, this R180 will exist only when n is even, right? And when it exists, it can definitely commute. Okay, so that is our idea. Now, uh, uh, what have we done so far? So, first we took the rotations, okay, and we studied the rotations alone, and we saw that all the rotations among them they will commute. Okay, so there we don't have any filter. Okay, now we took rotations and we studied how it interacts with the reflections. So we studied that the only rotations that will commute with the reflection is R0 and R180. Okay, so the candidates for the elements in center from rotations, the only rotations that can be in the center are R0 and R180 degree. Possibly. Here R180 may not exist always, but whenever it exists, it can be there in Z of dn. Okay. So we have talked about the rotations. We have talked about the contributions from the rotations. Now what about reflections? Can a reflection be in the center of dn? Answer is no, right? Because here we supposed that suppose R is commuting with F, then it will impose that R must be equal to R inverse. Now that is R must be one of them. So consider R consider rotation R, consider a rotation R such that R is not equal to R0 and R is not equal to R180. Okay, now such a rotation will exist, right? Such a rotation R will exist. In that case, can FR be equal to RF? This cannot be, right? Because from the earlier discussion, if FR is equal to RF, suppose there is a commuting, then R must be equal to R inverse and R must be equal to R0 or R180. So if we are considering some other rotation, then RF cannot be equal to FR. So F does not commute with R, right? So F cannot commute with R. So a reflection F cannot be in Z of dn. Okay, so uh, we have studied the rotations and reflections. We have exhausted everything. Okay, so what can Z of Dn be? It can be the only possible candidates are R0 and R180, right? And when will R180 exist? Only when uh, n is even. So when n is even, we will have that the center will have two elements, R0 and R180. But when n is odd, we will have that it is singleton R0. So this is exactly what we wanted to prove, right? The center of Dn is this.